around the world, Professor DK Liu, to give us, the talk on, in our, webinar. And first of all, I would like to introduce myself. My name is Hai, and I'm currently working at Murdoch University and serving as the academic chair of, instrumentation control engineering and industrial computer system engineering at, an engineering department. And I served as the, the IESWA chapter, the chair of IESWA chapter in 2020. And today I will be the host for, this webinar. And I hope everyone will enjoy, today's seminar. So now, before Professor DK give us, the presentation, I would like to have a very quick, brief introduction for Professor DK. Professor DK is distinguished professor and director of the Robotics Institute at the University of Technology, Sydney, Australia. His current research interest is robotics, with a focus on perception, motion planning, human-robot collaboration, and robotic systems. He has published many papers in RTB transactions, including transactions on robotics, etc. So besides conducting fundamental robotics research, he has also been transforming robotics research to practical applications. Actually, this is the most significant work Professor DK has achieved in the past few years, and including autonomous robots for steel bridge maintenance, bike-inspired climbing robots, etc. Since 2006, his research has received over 20 Best Paper and Research Engineering Excellence Awards, including the 2019 UTS Medal for Research Impact, the 2019 SME DET Leonardo Award, and so many other, well-known awards around the world. Part of his research outcomes has been translated to industry applications, including autonomous bridge maintenance robots commercialized by SABRE Autonomous Solutions, and many other, the practical applications. So now I would like to, welcome Professor DK Liu to give us the presentations. So if you have any question, please feel free to, to ask your question during the questions and answer, section. So welcome, Professor DK. Thank you. Professor DK, so possibly you have muted your microphone. Now, okay. Yeah, nice, okay.
Okay, yeah, thank you very much, Dr. Wang. And it is my pleasure to discuss with all of you about intelligent robotics research. Okay, so we know many tasks in our industry have been automated, like from manual to fully automatic. But there are still many tasks which have not been automated yet. People are still doing this kind of very difficult job. You can see here in manufacturing, to prepare the surfaces of various components, or even in the maintenance, and people are still doing this kind of difficult jobs. So for this kind of tasks, it's very difficult to automate. In infrastructure like bridges, for maintaining the bridges like the Sydney Harbour Bridge, people are still doing the work in this environment. And for example here, what you can see, the video shows two people doing the cleaning and removing the rust and the old paint from the surfaces before doing the painting. So this kind of task is very dangerous and very risky for people. Speaking of infrastructure, like what you can see here, people have been doing such dangerous jobs here. And for example, inspecting of the bridges, inspecting of the confined space, it's very difficult. and it's always dangerous. For underwater structure here as well, for underwater bridge piles, for example, like this one, or underwater pipes, so they are covered by marine growth. In order to do inspection, divers are asked to remove the marine growth before they're doing the inspection. So, but removing the marine growth is very difficult. You can see from the video here, it's very, very difficult and very, very dangerous for people to do this work. But unfortunately, in the whole world, people are still doing such kind of jobs because there are no other options at the moment. Transmission towers, you have been saying this in many places. People are still doing this, doing the maintenance, inspection and maintenance of this transmission towers. You can imagine how difficult and how dangerous for people to do this work. And also, it's very costly as well. In aged care, health care, for aged people to move around or to move patient from bed to wheelchair or from wheelchair to other places, still people are doing this work. You can see here, the nurses are doing this labor-intensive tasks. Assembly in many industry environment and inspection as well, and people have to do the work because the current systems are not good enough to provide the good result and also for the assembly in very challenging environment like this one. The critical issues here include the health and safety for the people working in such environment, and also the cost is very high, productivity is very low. So as a researcher in robotics and in mechatronics, we naturally think whether we can develop a robot to help or to do tasks, to this kind of tasks. But if we can have a robot to do such jobs, then the robot needs to be capable of operating in environments like unstructured, very complex, cluttered environment, unknown or partially known environment, or dynamically changing, or if it is in the underwater environment, then there's a strong water current, but if it is in the transmission tower, there's a strong wind as well. So you can see the challenges here. There is a big difference between robots operating in such challenging environment comparing to robots operating in factory or in indoor environment. So another challenge for robots to be capable enough to work for automating many tasks is for robots to work together with people. But this is even more challenging because when robots are asked to work together with people, and then the robots have to understand the people before they can really work together with people. So this is even harder. So by saying that, for robotics research, we can focus on two big problems. One is the fully autonomous robot. We develop robots or develop methodologies that can enable robots to operate in such environment fully autonomously. Another topic here is we develop robots that are intelligent enough to work together with people. Then we combine the strengths of people with the strengths of robots. So this is what we call the robotic co-worker or human-robot collaboration. So my research basically covered these two topics here. So I will explain the research work we have been doing here and also some applications in my talk today. So there are many research questions, as I explained before. My research here mainly answers those three big questions here. One is about the capability of robots. So how can a robot move and support itself in such complex infrastructure environment? Second is intelligence of the robot, including the sensor perception, environmental or operation awareness, planning, and also level of autonomy. What kind of, how much intelligence you like a robot to be able to do such tasks, and learning as well. Third question I've been trying to answer here is really how can we develop methodologies that enable robots to work together with people. And my research here is more focused on human-robot collaboration and also how information is used and also how robots working together. So, okay, so today, those are the two topics I've been talking about. The first one is about the robots in unknown and the complex environment. So the first thing we need to know here is that for the environment, like what you have said, you can say here, confined space with rivers everywhere, or very complex environment, or complicated structure here, or you can say this kind of structure or this transmitting towers. So the first thing is really, can we design a robot which is capable enough to move around in such complex environment? So you can look at you can get some idea from biological systems, for example, ants. So we did an experiment to investigate how ants just climb and also cross from the different objects, and also how ants do the transfer from the vertical surface to the horizontal surface. So we did a lot of research here, and then by the time we start to design a robot which can be capable enough to move around such environment, and at the same time to carry sensors or tools to do the cleaning and painting or other tasks. By the end, we found there's no such engineering technologies which can help us really to develop a robot which has the same similar capability of ants. So another thing we look at here, or you can think of here, is about inchworm. So you can see the inchworm, there are two feet there, and then we can learn from how inchworm moves around, then we design a robot. You can see here, this is the design of the robot, and which has a similar way to move around like an inchworm. So, but again, there are many challenges as well. If you want to develop a robot to have similar kind of capability like an inchworm to move around, it's still a challenge as well. Birds as well. We know birds is very good at climbing, is a very good climber, but it's very, very challenging to develop a robot which has the similar capability of a bird. And the reason we did this research here is really we like to develop a robot which is capable enough to climb a truss structure like the transmitting tower. So you can see when the bird is climbing, they use the 2 feet. At the same time, they use the beak. But birds can do this, but to develop a robot that is capable enough is very challenging. But when we look at the people climbing, like the rock climbing or just people climbing transmission towers like this, and we did a lot of research here and trying to find out how people do the climbing and also how they make their decision. Then we try to learn from people climbing for development of robots. So this is what we've been doing. So all this studies here is really trying to find out what is the optimal way or the best way to develop a robot which can do the tasks. So again, those are the research questions which have not been really answered yet. So if you are interested, those are the topics you can think of. So definitely it's quite interesting research there. The second is about sensor and perception. Like we said, mentioned in this environment, not only for the geometry, but also for the details. Because if you just only want to know the geometry or the surfaces, then that is relatively easy. But you really want to know the details and also the colors, the rivers, or the connections, then that's difficult because of the accuracy and because of the environment. And also surface conditions as well, and the location as well. So you need to know it is. So for many structures, you may find out a way to find the location, but for the confined space, because the inside is quite thin, it's very similar, and all the areas are the same, then how can you know where the robot is or where the surface is in that particular confined space, for example? So there are many ways to do this, and we have been doing this as well. And really, just you can see what you can see here is basically two different types of robots implementing the exploration algorithms we developed to build a 3D map of a complex structural environment. This one is in the market environment in our research lab, and this is the robot in the real bridge, basically in the Sydney Harbour Bridge, to build the map. You can see here. As I mentioned, find the locations are another issue as well, besides building this 3D map. So this is the robot doing localization and mapping in the confined space in the bridge structure. We need to know the details of the structure as well, not only the surfaces, but also the corners. And also we need to know the normals of a corner or the small surfaces as well, because we like to use this normal information, the red line here, and then to plan the robot to clean or to paint that particular surface. So in that case, we need to know the normals as well. So again, if you just only want to know the geometry, then it's relatively easier. But if you really want to know the details, then it is more challenging. Another scenario here is for different robots, like what you can see here, this is the naked robot in a confined space, like this confined space, with many rivers. And the robot itself is relatively heavy, for example, about 25 kilos. Once the robot starts to move, it may deform. If it deforms, then the sensor information is not accurate and a lot of uncertainties. So then how can you use that sensor information to get the good map, particularly to identify where the rivers are, for example, in this environment? Again, you need to have a very efficient algorithms to do this. Underwater environment is another challenge here. You can see this is a robot in the bridge structure. Try to build the 3D map of the bridge pile. And based on the information collected by the robot, then the robot will identify what kind of marine growth covered the bridge pile. Again, this is about construct a 3D map of a bridge pile. So third topic here is about planning. So planning has been topic studied very, very well and for many, many years. But there are still many challenges there. For example, what you can see here, if we can have the robot here really to go through the small hole in the real environment and also has to avoid collision with the surfaces or obstacles around. So it is still challenging. And also the challenges here is one is about has to be in real time or efficiently enough. Second one the path has to be smooth enough. Collision free, of course, has to be safe from the safety of the robot point of view. So a lot of challenges there as well. Of course, if you are not concerned of the efficiency, you can find a way to plan the robot. But if you do concern of the efficiency, then the challenge is different. And here, for example, when the robot just starts to, the robot wants to go through this small hole, and then the robot has to avoid step onto the river and also transfer, and then from one side of the small hole to the other side. So if everything has to be done by the robot itself, not manually controlled by human operators, then it is still challenging. Again, you can see this environment. This is in the real environment, and you can see the rocks and the surfaces the rivers as well. So real-time planning, and particularly for the transfer, is challenging. So this requires very good planning algorithms that can really be efficient enough and plan the optimal path for a robot to move around. And here is another example. If you are going to have this robot to go through the small hole here, the manhole here, and you have the rivers around, how you are going to really plan the robot to go through this hole. Besides the design challenges here. And you can say this is one of our robots designed for maintenance of confined space. Underwater environment. If the environment in underwater is quite complex, for example, many steel bridges and the other structures there, then getting the robot around, particularly if the robot has the manipulator on a mobile platform, and also there is the water current. In that case, the planning or the planner of the robot has to be good enough. So again, doing this kind of motion planning is still a big issue. Coverage planning. If you want to have one robot or many robots working in the real environment to clean the surfaces, for example, or to maintain a bridge or to maintain an underwater structure, then complete coverage or coverage planning is another challenge. So many robots are working together, or even with one robot to do the job. Then in that case, you need to move the robot from a location to another location. Then how you are going to optimize the base locations? So then this is the one you really look at, say, how can we do the planning to cover the area as much as possible, or what is we call it complete coverage or coverage planning. So I just mentioned some of the research work we've been doing here, and also to answer some of the research questions. So we have been applying those research outcomes into the development of different types of robots. Here, I'd like to talk about several examples here. The first one is that for steel bridge maintenance. So we developed a robot which can be used for steel bridge maintenance. And this robot has been deployed in real environment. And you can see this is the robot we developed. And you just put the robot into the environment and press the button. That's what you need to do. Then the robot will just use the sensor to scan the environment and then build a 3D map. Based on the map build, the robot will use the knowledge to improve the quality of the map. And after the map is ready, then the robot starts to do planning. So this is the planning stage. Then after the planning is done, then the robot will start to do the cleaning by using high pressure air and the garnet to clean the surface, to remove the old paint and the rust. Even with this bright surface, like the I-beams or the surface on the roof, the robot needs to be able to find a best way to clean that surface. Otherwise, the quality will not be good enough. So this is one of the robots we developed, and this robot has been deployed in real application and has been commercialized. Second one is climbing robot for confined space inspection. The robot can be put through a small hole like this. Then the robot uses a sensor to find out which way is the safer way to go ahead. For this application environment, the robot finds the sidewall does not have rivers. Then the robot decides to go through from this end to this end on the sidewall. And once the robot finds a hole here, then the robot needs to plan the motion of the robot and then to transfer from one side of the hull to the other side. And after the task is done, the robot comes back. So again, this is the fully autonomous robot, and it has been tested many times in the Sydney Harbour Bridge. For your information, the length of the arches or the confined space in the Harbour Bridge is about 7.2 kilometers. So you can imagine how useful this robot for the inspection of this Harbour Bridge. And also for this kind of application environment, people are not allowed to get inside of the confined space because of the safety concern. Then after the robot find in the confined space, if the maintenance is needed, but the climbing robot you saw before cannot do the cleaning and painting and the vacuuming. So then we developed another robot to do the cleaning, vacuuming, and the painting. So of course the robot gets to be able to move around, like what you can see here from the video. And also robot gets to be able to knowledge of the environment and localize it itself, then find the areas to clean. And also when the robot is moving, make sure try to step onto the rivers. So this robot has been developed. You can see this is the cleaning here, use the high pressure air and sand to clean the surface. And this is about vacuuming and also painting as well. So this is the third robot or third applications. So we developed an underwater robot for underwater structure cleaning and inspection as well. And here is the underwater version. This is one of the versions of the underwater robot we developed. So this robot has been extensively tested in the water tank in our research lab. This is in our research lab, and also tested in many steel bridges. In many bridges around Sydney. And this is the bridge in the North Sydney, and the robot just move around the pier up and down to build the map. And after the map is built, then identify the surface condition or identify the marine growth. After that, do the planning, then do the cleaning. It's fully autonomous, so people do not have to really interact with the robot if the robot is doing everything in the right way. So what people need to do is really just stay and monitor the operation of the robot. And if the robot is doing something wrong, then people will just control it. You can say this is what the people are just use a monitor or screen here to watch what the robot is doing. So again, this robot is ready, and several companies are talking to UTS about the commercialization of this robot for many different applications. Okay, transmission towers. We've been developing robots which can climb transmission towers like this kind of structure, and they then just use the sensors for inspection and use the tools to remove old paint and the rust and do the painting. So this project is about this is a 5-year project. We've been working together with industry companies. So and we still have about a year to go. So the progress of this project is good. What you can see here is a 4D robot, which will climb a transmission tower or truss structure. But this robot is basically really a research platform. Right now, we're developing a different robot which can really do the cleaning, painting, and the inspection. The new robot we're developing will be deployed next year in Japan for maintenance of power transmission towers. The laser system will be used for the cleaning. Another robot we're developing here is really for underwater inspection and measurement, particularly if the access to the underwater environment is very limited. For example, you just only have a small hole here. Then how can you really just develop a robot which can be put into the underwater environment underneath the structure and then use the sensor to do the measurement? And because of the water current, navigation is the issue. And localization is another issue as well. And also, when the robot is doing the measurement, for example, the sensor here to measure the to the measurement, then the robot has to be stable for a certain amount of time. But because of the water current, then it is challenging. So there are many things we need to look at. Control is one thing, but control is not the only thing which can solve the problem. The best way to look at the best way to solve the problem is control, design, and sensing. So has to be a combination of all these possible methods. Okay, so this is the first topic I like to cover into this talk. The second topic, I will just spend 10 minutes to talk about the second topic. This topic is about physical human-robot collaboration. So you can see here, if you have a robot, in different types of robot, then if you have a person here, and the person working together with this robot, and then we combine the strength of the person with the strength of the robot. This has a very, very significant or very big impact into many, many industry sectors in the future. And right now, there have been a lot of research in the world really try to develop robots which are intelligent enough to work together with people. But this is a long journey. So we need to do a lot more research works before we can really get the robot ready for real applications. So this is a very good topic if you are interested to research. We have seen some robots working together with people, but for very specific tasks. I will talk about several examples or several robots we have developed for very specific tasks. So, but in order to develop a robot working together with people, there's so many challenges we have not answered yet. For example, we really need to have human models, like human factors, like the brain. The brain model, like the muscle or the biomechanics model, for example. And also we need to know how much assistance a robot should provide to a person. So because people are different, you need to work out the right amount of assistance for a particular user. You need to keep the user or the person in the loop, and also very active, very engaged. Otherwise, it is very dangerous when people are working together with robots. So how a robot is going to trust a human user, or how a human user is going to trust a robot, to make sure both are doing the right thing. If one of them is doing the wrong thing, what are we going to do? This is what we call role change. So kind of dynamic change in the role of each party is playing. So again, it's challenging because the interaction is changing as well from time to time. For example, if you work together with a robot for 8 hours, then your interaction or your collaboration with the robot changes from the morning to the afternoon. So how can we adapt or find or identify this kind of changes and then incorporate these changes into the control or collaboration? So brain-robot interface, this is another topic you may be interested, and why I think this is a very good topic. Because brain, if you use the EEG signals, then you can find the user intention a little earlier than when you use the cameras or EMG sensor to measure the muscle activities, use the cameras to measure the body movement. Because if you can get the brain information, then that will help really improve the human-robot collaboration. So those are the research topics we have been doing here. So okay, let me go through this very quickly. Sensing. which is one thing. For example, sensing in the indoor environment, in the lab environment, this is easy. But if you want to sense in the mining environment or in a very dusty environment, then it's not easy. So, for example, we did an experiment in the blasting chamber, and we either use a garnet or use a steel grid. Then we just have a sensor to find out the pulse of the operator. We found this very challenging. Then we can work out in a different way. For example, if the sensor information is not enough, then can we just use other methods to combine the sensor information with other information, for example, the body we may have. So here's one example. We can just use the parallel mechanism, because you can say the human upper limbs are redundant systems, plus the torso as well. So you can just say when the robot is working together, or human is working together with the robot, then we assume the two hands are fixed, or we know the position of the two hands. So if that is the case, then we can just say assume the torso is consisting of two parts here. As long as we have algorithms to get these two parts together in a nice way, then we can work out the pose of the upper limbs. Then based on the pose of the upper limbs, then we can work out the strength of the human user. So this is about the strength of the human user. So for example, if a pose is like this, then we can calculate the strength here based on the biomechanics model. And if you have, for example, some part of the muscle in your shoulder is in fatigue, for example, then your strength is changed. But if you have a good model, then you can use this model to calculate the strength, and then use the strength to control the robot to make sure the robot provides the right amount of support in the right direction of support. So again, this is about strength estimation. So then after you know the strength, you know the pose of the human operator, then this next thing is that how much assistance a robot should provide to a user. For example, if this is the required capability, and this is the capability of the worker, and then the yellow part is the gap. And this gap is what is supposed to be provided by a robot. This is the ideal case. It's not ideal, it's a better case. So if we can do research to control a robot to provide this support, then the human-robot collaboration will be much more smoother, safer, and intuitive. That is what we want to achieve. So in that case, we will have a task model and the human strength model, and then based on these two models, we calculate the assistance required. Then we control the robot to provide the assistance. So, and also perception as well. When you can say when a human operator collaborates with a robot, the way the human holds the robot is another piece of information we can use to identify to know the collaboration, and also to learn the intention, to learn whether the person is really engaged with the robot or not in real applications. So, and control is another issue, but the control you can use what is available. For example, admittance control or impedance control. You just use what is available. Control is not that challenging when you have a robot there to working together with people. But more challenging is really the models. So another topic is about the confidence. As I mentioned, what is the confidence of a human operator in robot, or what is the confidence of a robot in human cooperators? So the confidence really is important because people make mistakes, and the robot makes mistakes as well. Particularly if one of them is making mistakes, what do we need to do? This is quite important. This is again safety as well, and also interaction or collaboration. Singularity is another issue. For example, if the robot is running by itself, Of course, you can plan the robot and control the robot to avoid the robot getting into singularity. But if the robot is working together with people, then the people, the robot needs to really know the people and to follow what the people want to, the operator wants to do. Then that is the problem. Then that is the big problem, because the operator always wants to move as much as they want, right? And always just over the limit of the robot. So in that case, you really need to handle this the singularity. So there is a paper published in TOR and about the handling singularity. So this is the important topic. Safety. You may have heard that COBOT providing the safety, but that kind of safety is a lower level safety. And in many applications, based on my understanding, that kind of safety is not enough. It's not enough. So if you want to develop a robot which can really work together with people, with different people, for example, 80 people, normal people, kids, ladies, or other people, for example, then you really need to have higher level safety measures implemented. Otherwise, the system will not be that good enough. So you can say safety by a system paradigm, or safety by interaction design, safety by sensing environmental awareness, and by control, of course, by design, and also by redundancy. So this is what we have been implementing in the robot we're developing. So it's quite important. But are those safety measures good enough? My answer here is really no, because for different applications, there are different requirements. So we really need to be focused more on the safety if you want to have a robot working together with people. Okay, so we have been applying the fundamental robotics research in physical human-robot collaboration into the development of several robotic systems. Here is one of them. This is the collaborative robot we developed for surface preparation, and you can see this is the interaction between a user and this robot, and this is the experiment just for testing the robot, whether it is capable enough for collision avoidance and how smoothly the robot is following the motion of the human. So this robot has been, okay, we talk about the strengths and the control as well, safety as well. So this is really testing in the lab environment. And this is the robot used by a blaster in the blast chamber. You can see the environment. And by the end, the results are quite good. So this robot is ready for a company to take over for real applications. So another one is about a robot we developed here to move patients from bed to wheelchair or from wheelchair to other places. So the nurses are using this robot and to move the patient, and it's quite smooth and quite intuitive when the nurses are using it. Without this robot, then two nurses have to move the patient. That is very difficult task. Many nurses get the lower back injury because of using the hoist and to move patient. So this robot has been tested in a nursing home for about a year. So it's quite good. Of course, we are trying to improve it as well right now. So exoskeletons, either passive or active exoskeletons with many degrees of freedom or smaller number of degrees of freedom, depending on the applications. So those are the things we've been developing, but those are the robotic systems we've been developing, mainly for testing the research outcomes we've been we're doing here. So, for example, we are right now we have ARC-DP for discovery project, which is about brain-robot interaction. So we're really trying to do a lot of experiment and research, try to improve the interaction between human and robot, and allow them to work together for real industry applications. Okay, so I guess this is about my talk today, and I'd like to acknowledge or thanks to many companies and the funding providers who provided the resources for the research work we've been doing here, and also many researchers who have worked with us in the last many years. Thank you very much, and you are welcome. And if you have any questions, thank you.
All right, thank you. Many thanks for Professor DK's wonderful presentations today. And not only from the theory part, but also particularly from the practical applications. So yeah, most of the slides from the Professor DK's presentations, he provided us with many kinds of interesting practical examples and applications. I believe this should have given all of the participants good motivations and inspirations for the future researchers. And from our audience, if you do you have any questions in terms of the robotics and mechatronics, and please feel free to discuss with Professor DK. As you can see, Professor DK has done many years researches on those areas. So this could be a very precious opportunity for us to have a discussion with Professor DK. Yeah. Okay, so if you have any question, now is the questions and answers time.
So there's a question here about the sensing environment.
Yep.
May I know a little bit more about the question?
So I hope well. So you raise a question regarding sensing environment. So can you please go, provide more details about your questions?
Hello?
Yes, we can hear you, yes.
Yes, my question is, let's say you want a robot to collect litter, and you want it to also know what litter to collect while it's moving around and collecting the litter. It's to just remove the problem on just litter. Yeah.
Yeah.
Like so, it has to also see the surroundings, that it's not going to hit a certain area. It's going to not dodge certain objects, but at the same time collecting specific litter.
Yes. So so what is exactly your question? So your question is about maybe could it be how the robot can do it, or what kind of sensor we can use, or?
Yes, the sensors. What would you use for that situation?
Okay, so if this is your question, this really and there are many things you probably need to think about first before we answer this question. For example, one is about, is that in the sunny day, is it outdoor or indoor, right? Or is the sunny day? Sorry.
Sorry. I thought it was a question.
Okay, yeah, that's right. Yes. So we need to know the environment first, and if this, for example, is in the sunny days and in the outdoor environment, or it could be the indoor environment, or could be in the underwater environment, for example. So we need to know this. Second one, because the sensors, you need to use different sensors for different applications. Second one is really about the environment. Whether this leader is really, for example, in the bush or in other places. So again, that is something you need to consider as well. So, and then after that, you can use the vision-based or use the laser-based or use other RGBD sensors, for example, to identify it. But if you can only see part of the litter or the rubbish, for example, then you need to just use some algorithms to get the whole, not get enough knowledge of the object. After that, you need to work out how you can just pick up it. Is that heavy? Is that soft? Is that round? Or is that kind of different material? So there are many questions, I guess.
Okay. Thank you.
Yeah.
Thank you, Professor DK. Is any questions from our audience? I believe most of our audience are from the robotics and mechatronics areas or control engineering areas. So now, please feel free to ask any question if you have. Yep.
I guess in my presentation today, I was really trying to probably talk about many research questions there. And although I was trying to provide a solution which is related to what we have been doing here, but again, does not mean that solution is good enough. So there are so many other ways you can just go to address the same problem. So,
yeah, exactly.
Yeah, so yeah.
Okay, thank you, Lika. Yuhao, do you have one question?
Hello?
Yes.
Yeah, we can hear you, yeah.
Okay. Many thanks for Dr. Liu. It's an excellent presentation. I got a question. I'm curious about the human-like climbing robot.
Yes.
I can see that it's a quite complicated structure, and I wonder how does it work? I mean, how can we control, so many actors, so many senses, and how does it climbing? And I want more maybe details, like how does it climb the tower and something like that.
Yes, definitely it's challenging. Definitely it's challenging. The challenging both from research and engineering as well. So let's talk about the research challenge first, then we'll talk about engineering. If we talk about the research aspect, I mean, really, when people do the climbing, because they use the knowledge they have, and people are very, very capable. And when you have a robot do the climbing, there are so many questions you need to answer. That is what, okay. Let's probably talk about the challenges I have had so far. Right? So then first one is really how the decision is made for the climbing. Second one is about, because the environment changes, the tower, for example, the truss structure, the changes from this one to the other one, right? And then how can the robot really just try to get the knowledge of the environment as soon as possible, and then work out the way to really to do the to climb. Third one is really about the safety. And if you want to have robot to climb it, and you really need to make sure the robot is safe enough, it's not going to fall, for example, right? So all this are from the application point of view, but those application challenges really, give us so much challenges for research. So that's why we start to look at how birds climb a structure or the tree, and also how people do the climbing. So that's the main reason we were trying to doing research about the human climbing for birds climbing. So we were hoping to learn something from studying human climbing and birds climbing. So this is from the engineering, from the research side. One more question from the research side as well is that whether you like to have a fully autonomous robot to do the climbing, or you like to have a remotely controlled robot to do the climbing, or you like to have a semi-autonomous robot. So again, this is about the level of autonomy. So this is another challenge as well. So this is about the research challenges. Then challenges in engineering aspect is that you mentioned if you have 40 motors or 24 degrees of freedom, for example, then is that easy to control it? It's not easy to control it, but at least we have a way to control it from engineering point of view. But the more challenging here from engineering aspect is about the payload of each motor you are going to use. Just for example, you probably realize your shoulder is much stronger than your wrist, right? Then if you're going to have a robot with 4 limbs or 5 limbs to climb a tower, and the robot is heavy, then many times you may theoretically you like the 4 limbs to hold the force equally or to some extent, but in reality, in real application, it's not the case. So it's very difficult to find a joint or motor which has such kind of torque to weight ratio. You want to have biggest torque, maximum torque, and the minimum weight. But the current in the current motor market is very difficult to find it. Then you have to work out a different way to do it. So again, I say this, definitely there are many challenges. I totally agree with you. And that is why the project we've been doing this is about 4 years now. We're still struggling to come up with something
exactly.
which can be really useful.
Yeah, it's quite challenging, definitely.
Yeah.
Thank you, Professor Dikai. And one of our audience, Krishna, are you here?
Can you hear me?
Yeah. Please go ahead.
Thank you, Dr. Liu, for your wonderful presentation. My question is regarding how does the state of each robot represented in the state space? Does it just include the degrees of freedom, or does it include both semantic information of the environment as well in its state representation?
Sorry, I didn't get your question. Can you just repeat it?
Yeah, sure. So as all we know that the state representation of a robot will include all the position and the theta, chi, and alpha of the robot. That is the heading of the robot.
Okay, so you are saying the state of the robot.
Yes.
Okay.
Yeah. My question is for complex robots like the Inch robot or other kinds of robot that climb very unusual environments. Does it include semantic information of the environment also in its state space?
Okay. In order to know, I think knowing the joint position or the angles, or it's pretty easy because we have many sensors to use in each joint, right? So then I think from the robot itself point of view, we know the position from the kinematics. Then we know the pose of the robot at any time. So just like you have the industrial robot, for example, you always know the 6 degrees of freedom of the end effector, like X, Y, Z, and the 3 angles. You always know this. How can you know that? You basically based on the joint angles. Then just use the forward kinematics. Then you can just get to know the position of the end effector. So, but if you have like the Inch-1 robot in the real environment, again, the joints of the robot are rigid joints. So, and we have sensors there to measure the joint angles. Then, based on the kinematics, we know where the foot or the fate is, right? So, another question associated is really about the location of the robot in the environment. For example, if you have that robot to move around with rewards everywhere on the surface, then you really need to know the relative location of the rewards with the robot. So that is the challenge in some environment.
Oh, okay. So do you consider the semantic information as well to localize the robot in that kind of environments, say relative to objects in the scene?
That's right. You can use semantic information. For example, when people doing the mapping, they just have the point cloud map or geometric map, or they can just have the semantic map. So definitely you can use it. The question here is how this information can be used. Yeah. I think that's yeah.
Thank you, Professor.
Yeah, thank you.
All right, thank you, Professor Dikai. And is there any question from our audience? Okay, so if there's no question, I would like to raise a few questions. Yeah. So because my research team has just initialized a few research topics regarding the robotics, and after listening to Professor Dikai's presentations today, we know this is a really long journey to go for us. So I have a few questions. The first one is, because Professor Dikai has introduced a few, many interesting research topics about the intelligent robotic systems, and in terms of the navigation, perception, and motion control of mobile robot of the robots. So during the past decade, I believe the artificial intelligence and machine learning, this kind of technique, has been popularly used in the robotic systems. So so could you please give us some insight of how those kind of techniques can be the better used in those robotic systems, particularly from the practical application point of view? Yeah. Thank you.
Yeah, okay, thank you. Definitely AI or machine learning definitely is one of the very most useful tools which can be used in development of robotic systems. We have been doing this for a while now, and for example, for the disturbance rejection in for the underwater robot, we've been doing this and published some papers by using machine learning approach or algorithms. And also, we are for the human brain robot brain interaction. We've been using machine learning to know the features of from EEG signals and use that features to improve the human-robot collaboration. So we've been trying to use it. We have had several challenges here because machine learning, or that it can be very useful, for example, for many different applications if you have enough data. If you have enough data. So, but with robotic system here, the data is always not enough. For example, if you imagine the robot in the underwater environment, for example, right? And one is almost impossible to collect sufficient data for the learning algorithms to learn. And this is the first challenge. Second challenge is that the main reason is challenge here is really about the changing of the environment. The environment changes, so it's very difficult for you to collect enough data for every situation in the environment. So, but then we start looking at the transfer learning. So can we do simulation to real application learning? So we've been trying different ways, like what the machine learning researchers are doing, but still challenging. There's still many questions that need to be answered before we can really apply machine learning in robotic systems. Also, right now you can see so many papers about machine learning in robot motion planning, path planning, or whatever. There's so many just research, but if you talk to them, they have similar questions here, or similar comments like what I mentioned. It is challenging. Another challenge here is that, for example, if you are going to have the use machine learning or deep learning, whatever, for the image processor, for example, then it's relatively, the accuracy is good enough right now, is all right? But then they don't need a model. But if you're going to have the applied machine learning for robotic systems, then do you need a model? You like to have a model-free approach, or you like to have the model-based approach? So again, those are the questions people in the robotics community people have been trying to answer. Yeah.
Okay. Yep. Thank you very much, Professor Dukai. And my second question is, because you have introduced the one of the very interesting application of robots in power transmission towers, and I believe for you should have utilized the remote control for the robots, for the application of power transmission towers. And in this case, I would like to know, is any like the delay, when you design the remote control, and as well as from the communication point of view. So is there any delay in the practical applications? Yeah.
That is the question we have had before as well. Depend on, as I mentioned, this really depends on the level of autonomy of the robot. So if you really want to remotely control every motion of the robot or the motion of every joint in the robot, then that is very challenging. And the challenges mainly include one, the environment is complex, and also you cannot just perceive the environment very nicely in the field, right? Second one, as you said, the communication is the problem. So that's why personally, I do not suggest really to remotely control the robot in a very detailed way, like for example, to the motion of the joint level, for example. So I would suggest, this is what we've been doing here. We like to go for the robot with the semi-autonomous or fully autonomous. Fully autonomous, we understand, you put the robot into the tower, that's all you need to do. The robot is going to climb there and then come up and come down, right? So this is fully autonomous. Then between fully autonomous and the remote control, there is the middle, there is the version in the middle, what we call the semi-autonomous. So I do think the semi-autonomous is the right way to go ahead from the application point of view. But from research point of view, we can do many things, right? So the reason I think semi-autonomous is the right way is that in the semi-autonomous mode of operation, the human operator provides the high-level commands. Then the robot provides then the robot does the control action based on the high-level command from the operator. High-level command could be, for example, move left, or move up, move down, move right, for example. This kind of high-level command. Or move from point A to B. Point is not the point of each joint, it's about the point of the whole robot. Then after that, the robot is going to take actions. So this is the way I would reckon.
Okay, yeah, thank you very much, Professor Dikai. Yeah, because sometimes there's always a gap between the theory and practical applications. So yeah, so we have to find a very optimal way to solve these kind of technical problems. Yeah, thank you, Professor Dikai. And I think the time is up for today's presentations. And before we end today's session, I would like to say many thanks for Professor Dikai to give us a very excellent and the wonderful talk. And I believe everyone should have enjoyed a lot from today's presentations. And as you can see from your screen, so our webinar has been successfully recorded today. So in the future, if you would like to watch the video, please feel free to go to our YouTube channel of IEEE IES WA chapter. So if you have any question, I believe Professor Dikai would be welcome to to discuss with you. And thank you again for Professor Dikai to give us today's presentations. And I look forward to seeing everyone in our next month's webinar. So thank you, Professor Dikai, and take care. Thank you.
Thank you very much. It's my pleasure. Thank you. Take care.
Thank you. Thank you very much. Cheers. Bye. Bye.
Thank you. Bye.